Hey everyone, this is Joanne Panzardi. Some of you may know me already. I'm a little uncomfortable being filmed, so instead I just drew a picture of myself. Hope that's okay. You guys are coming into statics, and you're somewhat prepared to start statics from your Physics 4A class, where you learned about components and rigid bodies. But I find that the first 2 weeks of statics, I go over everything that would make you successful in statics, and I wound up spending too much time. So the first week of school in the spring semester in statics, I want to do statics. So instead of teaching you, spending 2 weeks reviewing and getting you up to speed on what you need to be successful in statics, I decided this time that I would actually tape myself teaching that part and then give it to you a couple of weeks before school starts so that you can prep, and you're going to be asked to do one homework assignment. So this is a way that you're going to be better prepared for statics, and then during the statics semester we could spend more time on statics rather on reviewing what you already know. So, okay, so here we go. So the main topic that we're covering is resolving forces into components. And I know you know it already, but I'm going to teach you how you do it as an engineer and not as a physicist and a mathematician. Because you guys took physics, you took math, you know how a mathematician talks, you know how a physicist talks, but now we're going to learn how the engineers communicate. So to start out, I'm going to start with the way you learn things. So here's our positive x-axis, here's our positive y-axis. And we have a force that we're going to call F. And we're going to start knowing an angle. So let's call this theta. So in order to find the force in the x, you're going to tell me that force in the x is equal to force times the cosine of theta. And you're going to say that force in the y is equal to force sine theta. You're going to come to find out, and I'll tell you probably the first week of school rather than during this taping, that as engineers we want to use cosine. We don't want to use sine. There are 3 reasons, and we'll talk about it later. So first I want to let you know that in statics we call theta x the angle between the force in question and the positive x-axis. And as you would expect, the angle between the force in question and the positive y-axis is theta y. So rather than doing it in this way, what we're going to say instead is that fx is equal to f times the cosine of theta x. And fy is equal to f times what? The cosine of theta y. In this case, we're making sure that we're using the cosine. Okay. Now, this is the case if they give you an angle. This is my representation of an angle. This is solving for forces into components using an angle. Well, what if they don't give you an angle? Instead, let's say they're giving you distances. So let's do it a little bit differently. So on both these 2 problems, we're looking at 2-dimensional problems. We have our positive x and y. We have our force here. And instead of giving us an angle, they're saying that the dimension in the x is 3, the dimension in the y is 4. Now, in terms of physics, what I've found, students coming from physics, the first thing that you'll do is find out what this x is here. What do we call this x in statics as engineers? We call it theta x. You find that angle. But there's 2 reasons why not to do it. 1, it's a waste of time, and time's money. 2, you're going to wind up getting a value that's carried out to, could be 7, 8, I don't know how many decimal places are, and you're going to wind up having a rounding error. So instead of finding the angle, instead what we're going to do is we're going to just look at this in terms of the ratio. We know that if this is 3 and this is 4, we know the hypotenuse of that triangle is 5. And let's take a look at similar triangles. We have a 3, 4, 5 triangle. And then we have another triangle that's represented by our force, the hypotenuse of the force, we have the force X here and the force Y here. And using similar angles, you could say, similar triangles rather, you could say 3 is to 5 as Fx is equal to F, right? 3 is in the X direction, 3 is to 5 is the hypotenuse, is equal to Fx over F. So in the end, we could say, well, Fx is equal to 3, the distance in the X, over the hypotenuse times the force. And then the same thing you could do with Fy. Fy is the distance in the Y, which is 4, over the hypotenuse times F. And this is going to give you a more exact value for Fx and Fy than if you found out what that angle is. I think that angle is like 35.12, I don't remember what it was. Okay, so it's really important that when you are given angles, use the angles, the theta x and the theta y, to find the component. But if you're given distances, you're going to use ratios to determine the components instead. You're not going to go and find that angle. Okay, so I'm going to stop it and then move on. Okay, so now we're going to do an example. So we have a force of 350 newtons in the first quadrant, and we have an angle of 60 degrees. So first of all, what do we call this angle? It's the angle between the force in question and the positive x-axis, so it's called theta x. And where would theta y be? Theta y would be over here. Theta y represents the angle between the force in question and the positive y-axis. And what angle is theta y? 30 degrees. Rather than finding the x component of the force and then finding the y component of the force, we're going to be methodical and solve for it all at the same time. As engineers in our solutions, we want to be efficient with our time. So we're going to set it up and do it all at once. Okay. So F is equal to, we know that the magnitude is 350 newtons. And I'm going to put parentheses and I'm going to put my units out here. So I'm putting the magnitude of the force here. I'm putting my newtons, my units over here. And now I'm going to look at what is the x value. You're going to tell me that the x value of this force is 350 newtons times the cosine of 60 degrees. So I'm going to put the cosine of 60 degrees here, and I'm going to put I. Remember, I represents the vector in the x direction. Then, for the y component, my force, my component of my y component of the force is going to be 350 newtons times the cosine of 30 degrees. And I'm going to put j, because j represents my y. So if you look at this, this right here is my x component of my force. And, where's the green? This plus this is my y component of the force. Okay, so my first step is to have it in vector form with I and j, with the magnitude in front and the units in the back. Next step is, right, 350 still, that is my magnitude. And now I want to know what the cosine of 60 is. And what's the cosine of 60? It's 0.5, right? And I'm going to carry it out to 4 decimal places. Because in engineering, we carry things out to 4 decimal places. So 4 decimal places for this part. I just had an alarm go off, so I'm not sure what that was all about. So 350 times the cosine of 60, I carry it down, 0.5i. And what is the cosine of 30? What is it, 0.866? Yeah, 0.8660. Again, I'm putting 4 decimal places, j. So let's take a look at this now. 350 represents what? The magnitude of this force. What does this guy represent? We know the difference between magnitude and vector, right? A magnitude, a scalar and a vector. A scalar represents the magnitude, right? So the 350 only represents my magnitude part. It's the scalar part. But this right here represents our direction. Does anybody recognize what this would be called? It's telling me the direction in the x and the direction in the y of my force. It's my unit vector. So in engineering, when we go through these steps, our second step is actually expressing what our unit vector is. Okay? In engineering, we always represent what the unit vector is in decimal places, and we represent it in 4 decimal places. So we should probably have a little column right here that says rules. So first rule, unit vector, UV, has 4 decimal places. Always. First rule. Okay, now I could come through and write what the actual vector is. So 350 times 0.5 is going to be 175. And our rule is we always are going to represent forces. Our forces, which in this case we're looking at our components, are 1 decimal place more than what's given. So in this problem, what was given was 350 newtons. So we're going to have our solution, our component, 1 decimal place more. So 175.0 I plus 303.1 J. And then I have to make sure that I put my units at the end. So in the end now, we have found the component of the 2 forces, and we only had to do 3 steps. We started saying what the magnitude of the force is times the cosine of theta x, I, plus the cosine of theta y, j, and we put the units at the end. So this is how I want you to find things. I want you to do it this way because it's more methodical and it's more efficient. So then I carried down. Cosine of 60 is 0.5, carried out to 4 decimal places because unit vectors in statics and engineering are always in 4 decimal places. It's never left as a cosine of an angle, it's never left as a sine of an angle, and it's never left as a fraction. I know in math you left things as fractions. You might say, well, it's not so exact, Joanne. If you have a fraction or a cosine of an angle, that's more exact. You're rounding now. Well, in this case we're not, and I guess this case, but another case we might be. But it doesn't matter because we're going out 4 decimal places as it is. 4 decimal places is not going to give us any rounding error. So then I took the cosine of 30, I put it down here. So this is my unit vector of this force, and then I'm representing the force in the end in vector form. Okay. So there are a number of ways to represent a vector. To represent a vector, one way is in vector form. And somebody might say Cartesian vector form. Another way is magnitude and unit vector. So the magnitude of this force is 350 newtons, and the unit vector is 0.5123 I plus 0.8660 J. Are there any units associated with the unit vector? No. Unit vectors are unitless. They're giving us direction. The magnitude gives us the unit of the force. And another thing to realize is that engineers represent unit vectors with an E, which is kind of weird. I think in math it's a lambda, and I don't remember what it was in physics, but in engineering it's represented as E. So the first way to represent a vector is vector form. The second way to represent a vector is magnitude and unit vector. And the third way to represent a force, so this is one way to represent, let's write it in red. One way to represent a vector, another way to represent a vector, and the third way of representing a vector is magnitude, which we know it's 350 newtons, and what's referred to as the direction angles, and the direction angles are the theta. Theta x is 60 degrees, and theta y is 30 degrees. So we just represented this force in the 3 different ways we could represent a vector. And you need to know all 3 of these ways, because I'll ask you to represent it in one or all 3 of these ways. Okay, so what are the 2 rules so far? Unit vectors are represented with 4 decimal places. Forces are represented 1 decimal place more than given. Okay, I'm going to stop the tape again and then do another example. Okay, before we move on to the next problem, I just want to show you some checks that we're going to be needing to do too. What's really neat about statics is because it's so computational, there's going to be so many times that we could check our work. And checking our work is really important because if you check your work, then you know whether you got the right answer or not. So let's take a look at this. We represented a vector in vector form. We got 175.1 as the force in the x. We got 303.1 force in the y. Is there a way we could check this with our original force of 350? Couldn't we do it using Pythagorean's theorem, right? Can't we say that if I take 175.1 squared plus this is 0. This is 175, 0. 175.0 squared plus 303.1 squared under the radical, what should it be equal to? It should be equal to the 350. And if you try it on your calculator, you'll find out. And then you put a check and write OK next to it. Okay, we also represented the force as a magnitude and a unit vector. How can we check the unit vector? Well, a unit vector has a magnitude of 1 unit, 1, right? So can I say 0.5 squared plus 0.866 squared? I could put the radical if I want, but I don't need to because 1 under the radical is 1. This should equal 1. So again, check it on your calculator, and you should check it out. And it should. Then once it checks, you put a check and an OK. Okay? So we were able to check the forces, and we were able to check our unit vector. And we want to be able to do both of those. Another check isn't computational, but it's a visual check. So I'm going to do a plus or minus visual check. Let's take a look at the picture, the schematic that we're given initially, and say, we got a positive x value. Does it make sense that our x is positive? We got a positive y value. Does it make sense that this force has a positive y? And it does. So we did a visual plus or minus check, and I put a check mark with an OK. So we have 3 checks here. A visual check for the positive and negatives. We got a mathematical check for the magnitude of the force. And then we did a check on our unit vector. OK, now we'll move into the next problem. Okay, we're going to do another problem again. And still we're looking at a 2-dimensional problem, and we're also looking at an angle problem because they're giving us angles, they're not giving us the distances. And I kept the rules on the right side. Okay, so we're going to set it up the same way we did in an efficient manner. Our force is equal to, the magnitude is 400. We're going to put parentheses, and we're going to put the units at the end. So now, let's take a look at what our thetas are. So what's our theta x? Theta x represents the angle between the force in question and the positive x-axis. So it's 45. So I'm going to say cosine of 45. What is theta y? Well, let's take a look. It's that theta y represents the angle between the force in question and the positive y-axis. So what is that? That's 90 plus 45, that's 135. So again, theta y and theta x, which are called direction angles, represent the angle between the force in question and the positive x or y-axis. So in this case, we're looking for theta y. It's going to be the angle between this force and the y-axis, which is 135. So then I go cosine of 135j. So this comes out to 400 times 0.7071 minus 0.7071 J newtons. And this comes out to be 282.8 I minus 282.8 J newtons. And how are we representing our force right here? Remember, there are three ways to represent it. It is represented right here in vector form. So notice what happened. By using the cosine of 135, we're getting a negative value directly. And that's one of the reasons why cosine is so good. You don't have to remember to stick in that negative. If you use sine, you have to remember to stick in the negative. When you use cosine, you will always get the correct positive or negative sign. So since we did this in vector form, let's do the checks as we go along. So let's do one check. We have the 282.8 squared plus 282.8 squared. Under the radical, pull out your calculator, check it out, and it's going to equal 400. So it checks. We also want to do a positive negative visual check. We got it for the x component, we got a positive 282. That's correct. We should have a positive. And for the y, we got a negative. Should we have a negative? Yes, it's going in the negative y. So our visual check works as well. Okay, we represented it by vector form, but now we could also represent it with magnitude, right? Force is equal to 400 newtons. And the unit vector, remember, it's represented by E. And the unit vector is 0.7071I minus 0.7071J. So now, right here, we represented the vector in the second form. The first form was in vector form. The second one is magnitude and unit vector. And how can we check our unit vector? Well, it's 0.7071 squared plus 0.7071 squared, and it should equal 1. Remember, you don't have to put the radical because 1 under 1 is 1. So, okay, 1 under the radical is 1, I mean. So we represented the force in vector form. We represented the force in magnitude and unit vector. And what was the third way of representing the force? Do you remember? It was magnitude and the direction angles. So what's the magnitude? The magnitude is the force is equal to 400 newtons. And the direction angles, theta x and theta y. What was theta x? 45 degrees. And theta y was 135 degrees. So that was the third way of representing the vector. There's another check we could do, which is really the same as the check for the unit vector, but I'll write it down over here. I mean, basically, because you have the two direction angles, the cosine squared of theta x plus the cosine squared of theta y is going to be equal to 1, 2. And we'll put an OK. So the unit vector check and this check with the direction angles is really the same. But I mean, if you made a mistake going from the direction angles to the unit vectors, checking both of them would be helpful. Okay. I guess doing a tape lecture like this, I can't really take questions because there's nobody sitting out in the classroom with me. So I'm hoping that you'll email me questions. But I've taught this class enough to know what some questions are, so I'm going to look at those right now. I remember many times people saying, well, you said theta x is 45. Couldn't we have gone the other way? What is this angle right here? It would be 360 minus 45. So what's that? 315? 315 degrees. Actually, That's theta x2. This is the first time in your educational career, I think, where one variable could have two different values. Because the cosine of 45 is the exact same number as the cosine of 315. It's going to come out to a positive 0.7071. So theta x, you could go the shorter distance or you could go the longer distance. But they're still both represented as theta x. So you could have put theta x as 315 here if you wanted. It didn't matter. How about theta y? What's the other theta y? The other theta y is this, no? It still represents the angle between the force in question and the positive y-axis. And what angle is this? Well, this is 180 plus 45. 180 plus 45, that's 225. So that is also theta y. Theta y. And again, when we did cosine of theta y, right, this is theta y up here. This is theta x. If instead of going in this direction and putting in 135 for theta y, instead if we went around this direction and got 225, the cosine of 225 would have given you a negative 7071. So again, I'm pretty sure this is the first time where one value could actually have two different, one variable could actually have two different values. Okay, so let's just review. In both these examples, you were given a force, you were asked to find components, and you were given an angle. So we did it in a three-step process. The force is equal to the magnitude. We took the cosine of both angles, and we put the units at the end. We carried down the magnitude, we represented the unit vector in 4 decimal places, and then we represented the force in vector form. If you were also supposed to represent the force in magnitude and unit vector, you would have to write this here. And if you were also asked to represent the force in magnitude and direction angles, you would write this here. I just remembered another question that students have had in the past. And the question is, let's erase all this. The question was, when we represent the force with magnitude and direction angles, do we have to represent both? Or could we just say the force is equal to 400 newtons and theta x is equal to 45 degrees? Now that I gave you this description here that theta x and theta y could have two values, is this good enough? Can I have represented the vector only with its magnitude and theta x being 45 degrees? And the answer you probably figured out is no. Because if this is my positive x and y axis, theta x could be here and theta x could be here. So I could have this force here or here. So I cannot just give theta x. I have to give theta y as well, because then you know that it's not this location, it's got to be that location. Did everybody catch that? You have to represent, it's in a two-dimensional problem, you have to represent both thetas, because now we know that theta x could have two values and theta y could have two values. By giving the both values, I know where to pinpoint where that actual vector is. Okay, so the next problem we're going to do is doing still a two-dimensional problem, but we're going to do it using ratios, distances instead. Okay, I'm going to shut this off. Okay, I'm still keeping up the rules on the right side, and we're just going to keep adding to it. So now we're looking at a force of 500 pounds. Everybody hopefully knows that that means pounds. And in this case, there are no angles given. Instead, I'm calling this a ratio problem. instead of an angle problem. Because based on the distances, we're going to be able to find the components. And remember, we are not going to stop and find that angle to find the components. We're going to use the values. So for this triangle right here, we're looking at a 1 dimension in the x. We're looking at a dimension of 4 in the y. So what is the hypotenuse going to be? It's going to be 1 squared plus 4 squared under the radical. And it turns out to be 17. And we are going to keep it in that radical form. So now I'm putting in my 17 right here. And we're going to set this up the same way we set up the others. We're going to do it methodical. Force is equal to 500 is the magnitude. We're going to put the units at the end. But now, since we don't have angles, we're going to use ratios. I'm trying to find the x component. So the x component is going to be the distance in the x, 1, over the hypotenuse, which is radical 17. Right? So if I take 1 over radical 17 times 500, that's going to be my x component. And I'm going to put I. And then for the y, the distance in the y is 4. The hypotenuse is 17. And I'm going to say j. Notice, we're using the ratios. We're not using the cosine of the angles. We have to make sure that we're putting in positives or negatives. Is the x direction positive? Yes, it's positive. The y direction, is a positive? No, it's negative. So we have to put in a negative here. Okay? So just looking at this, isn't this what we did earlier? This is my fx value. And this is my fy. Remember, we looked at similar triangles, and you could go back on the tape and look back at that and see how we set up similar triangles between the distances that were given and our similar triangle of f, fx, and fy. 1 is to fy as radical 17 is to f. Okay, so then we go to the next step. F is equal to 500. Now I'm putting my unit vector. It turns out to be 2425i minus 9701j pounds. And then I carry this out and I get F is equal to 121.3 I minus 485.0 j pounds. And this is my vector. And how did I represent it? Vector form. So I just represented it in vector form. And can I do checks? Sure. I'm going to do a positive, negative check. The 221x should be positive, yes. The 485y should be negative, yes, it checks. I'm also going to do a magnitude check. 121.3 squared plus 485 squared under the radical, it equals 500, and it checks. Make sure when you do a check that you actually check, because if you just write you check, but you didn't check and you got a mistake, you're in the doghouse. Okay, so we checked the positive and negative, we checked this. Let's now represent our force as magnitude and unit vector. So the magnitude is 500 pounds, and the unit vector is 0.2425i plus 9701j. And remember, unit vector doesn't have any units, it's unitless. And how can we check this? 0.2425i plus 0.9701, squared, 0.2425 squared plus 0.9701 squared is going to equal to 1. And now we just check that. So we represented our vector in vector form. We represented it in magnitude and unit vector. And what was the third way we represent it? We represent it magnitude and direction angles. So let's look back at the picture. How could we get the direction angles? How could we get the direction angles? We know all the ratios, right? We know all the ratios. So if we're looking at theta x, where's theta x? Theta x is the angle between the force and the positive x-axis. And theta y is the angle between the force and the positive y-axis. There's actually a number of ways that we could do it. So I think what I'm going to do is erase the board here and let's write the different ways to do it because I don't have enough room right now. Okay, so I'm going to shut the tape off and erase it and then I'll do it. Okay, so I cleaned the board a little bit and we have our picture still up there of the 500 newtons going in the fourth quadrant. And I wrote down what we had before, which was the 500 units, 500 pounds, 500 pounds. And then we used the ratios in the x and the y. And from that we found out what the unit vector is. And from that we found out our force in vector form. So what we're trying to do now is find out what is theta x equal to and what is theta y equal to. And in statics there tends to be like 3 ways to do everything. I guess AutoCAD there's like 10 ways to do everything, but in statics typically we're looking at 3 ways. So at this point I would ask the class what are some suggestions they have, and so I'm just going to write them down. So one person might say, oh well, we could find theta x by saying it's the inverse cosine of fx over of f. And this is the case because the theta, cosine of theta x is equal to fx over f, right? We know that already. We know in order to find fx, it's going to be f times the cosine of theta x. So we could use this equation to solve for theta x. And then of course, so theta y would be equal to the inverse cosine of fy over f. So that's one way. Another person might say, well, why don't we just use the numbers we initially were given? So the cosine of theta x is really just equal to 1 over radical 17, and the cosine of theta y is equal to the negative 4 over radical 17. And that makes sense too, because remember, when we did have the angles, this area right here would get the cosine of theta x, and this would get the cosine of theta y. So isn't this just another way of expressing theta x? And then the third way, somebody might say, well, this transfers to my unit vector, so isn't just the cosine of theta x equal to the unit vector in the x, which in this case would be 0.2425. And the cosine of theta y would be equal to the negative 9701. Okay? And they're all going to give us almost exactly the same value. Actually, they will, because the third rule we're going to write up here is that we always express the direction angles, and even though we just talked about theta x and theta y right now, as you can imagine, when we get into 3D, there's actually going to be a theta z. They're always represented to 1 decimal place. So since we're representing angles to 1 decimal place, in the end, we're going to get the same value. So theta x turns out to be 76.0 degrees, and theta y turns out to be 104 degrees. So noticing now that you calculated theta x and theta y, can you see another way for a check? So I'm going to do it up here because we have a little bit of room. Isn't the cosine theta x squared plus the cosine of theta y squared equal to 1? So if we put the cosine of 76 squared plus the cosine of 104 squared, it should be equal to 1. And I do want to check it. So I'm going to put it on pause. I'm going to stop the tape, go check it, and then come back. Okay, so I did make a mistake. So whether I do solve for the cosine of theta y by saying the y component divided by the 500, or I do it using the ratios of the distances, or do it using the unit vector. The theta y turns out to be 165.7 degrees. And then my check would be cosine of theta x squared plus cosine of theta y squared equals 0. And sure enough, it checked. Okay, so at this point, we've solved, we've taken forces that were in 2 dimensions, and we solved for their components using both ratios and angles. And at this point, you can do homework 1. And I'm going to have homework 1 due the first day of class. So homework 1 is on page 6 of the packet, and the packet's on my website. Go to the my website, and then it's under Engineering 35, and it's on page 6 of the website, and it's asking you to solve for components x and y of 2D problems, and it's also asking you to do checks. Okay, great. Have fun. Bye.